will have our first platinum sponsor, Yodeck speech from Petros Lymperopoulos.
And the speech title is Unlocking the Power of Web Workers, Optimizing JavaScript Performance for Modern Web Applications.
Few words about Yodeck. Yodeck is a leading digital signage provider, powering over 90,000 screens globally, and they strive to provide a seamless and affordable digital signature solution. Market leaders such as Autodesk, Hydro, Ford, Adobe, Pizza Hut, Domino's, and Deloitte trust Yodeck for their digital signage strategy.
And a few things about Petros Lymperopoulos. He is a senior software engineer at Yodeck, where he contributes to the development of a web player that had been successfully ported across multiple operating systems. With a background in electrical and computer engineering from the University of Thessaly, and my university as well, and Labros University as well, Petros brings expertise in Android native development, contributing to Yodeck's versatile software solutions.
Let's welcome on stage Mr. Petros Lymperopoulos.
Hi, everyone. I'm Petros Lymperopoulos, a senior software engineer at Yodeck, where I've had the pleasure of working for the past 4 years. Yodeck is an intelligent digital signage platform designed for ambitious teams who want to revolutionize audience engagement. Founded in 2015, Yodeck started with just one test customer. In less than 5 years, we became the leading digital signage software in the world, with our core mission staying exactly the same: to offer professional, easy, and affordable digital signage to all. Yodeck is split into two key components. First, there's our web app, which allows users to manage their screens, assign new content, and utilize the power of our powerful features. Second, there is the player component, which takes the results of that process and displays what the user wants on the screens. I work on the player component, where we leverage web workers extensively to handle the complex tasks involved in delivering a smooth and seamless experience. Sorry. Okay, here we go. Today, Yodeck powers over 150,000 screens globally, serving more than 20,000 customers, and partnering with 650 resellers. We focus on simplicity and ease of use, helping businesses of all sizes, from single-screen setups to signage networks with thousands of screens. Our platform supports a wide range of operating systems, including Raspberry Pi, BrightSign, Tizen, WebOS, web browsers, Android, and Fire TV. Our achievements don't stop there. For the past 2 years in a row, Yodeck has been recognized as a great place to work. Our headquarters in Athens is home to an incredible team that drives innovation and delivers exceptional results. Market leaders like Adobe, Ford, Adidas, and Domino's Pizza trust us for their digital signage strategies, highlighting our commitment to reliability and quality. We aim to transform how organizations engage with their customers, employees, and stakeholders by harnessing the power of digital screens. Since digital signage might be new for many of you, let me explain. It's all about delivering content dynamically to displays. Think about the screens you see in stores, airports, or restaurants. Digital signage provides a seamless way to engage audiences, share information, and create impact. And today, I'll talk about how web workers have been a game changer in making this system smoother and more responsive. So, what exactly are web workers? Web workers are a way to run JavaScript in the background outside the main thread. This lets us offload resource-intensive tasks like complex calculation or data processing from the UI thread, which is crucial for maintaining smooth and responsive applications. In a single-thread environment like JavaScript, every task runs consecutively on the same thread. While this simplifies coding, it becomes a bottleneck for complex applications. Let's say you're working on a video editing tool in the browser. Tasks like processing video frames, applying filters, or encoding media can overwhelm the main thread, making the UI sluggish or even unresponsive. Web workers solve this by running these intensive operations in parallel threads. For instance, in a web-based game, web workers can calculate physics simulation or AI logic while the main thread handles rendering. For file handling, such as compressing or encrypting large files, web workers take on the heavy lifting without freezing the interface. By introducing parallelism, web workers make JavaScript more capable of handling demanding tasks. They don't share memory with the main thread, but communicate through serialized messages, making them efficient and safe for offloading work. Let's dive deeper into the core challenge of JavaScript's single-threaded nature. JavaScript was designed as a language for simple interactive behavior on web pages, where everything, UI updates, event handling, and computations runs on the same thread. This design works well for small-scale tasks, but quickly becomes a bottleneck as web applications grow in complexity. Modern applications, like real-time dashboards, interactive games, and web-based video editors demand much more from JavaScript. Imagine a scenario where a dashboard processes real-time stock market data while trying to render graphs and respond to user interaction. Without offloading tasks, the main thread becomes overloaded, causing delays and laggy visuals. Another example is a photo editing app applying filters to high-resolution images. If the main thread is tied up processing the image, the interface becomes unresponsive, frustrating the user. Similarly, in a collaborative tool like a real-time editor, managing and syncing large volumes of user data without introducing delay becomes almost impossible in a single-threaded environment. The result of these bottlenecks is what users experience as slow or frozen interfaces, stuttering animations, or even complete crashes. These issues are especially prominent in apps where responsiveness is critical, such as financial tools, gaming platforms, or multimedia editing software. To make matters worse, as the complexity of tasks grows, even basic interactions like scrolling or clicking can suffer delays if heavy computations are taking place on the main thread. Web workers address this limitation by introducing concurrencies into JavaScript. By moving computationally heavy tasks to separate threads, web workers free up the main thread to focus on interactions and UI rendering. This separation allows for a smooth and responsive experience even under heavy loads. For instance, while the main thread updates the UI and processes user inputs, a web worker can handle large data computations, real-time calculations, or even the processing of stream data. The end result is a seamless experience for users, where intensive operations happen quietly in the background without impacting the app's interactivity. By understanding the limitation of JavaScript's single-threaded nature and leveraging web workers to address them, we can build web applications that are not only fast, but are also resilient under demanding workloads. Let's take a closer look at how web workers function under the hood and how they integrate into web development. Web workers operate by creating separate threads within the browser JavaScript engine, allowing complex tasks to run independently of the main thread. A worker is created using the worker constructor, which takes a JavaScript file as an argument. This file contains the code the worker will execute. Communication between the main thread and the worker happens through a messaging system. The main thread sends data to the worker using post message, and the worker sends the results back in the same way. These messages are serialized, meaning they're lightweight, and ensure efficient data transfer. Web workers run in isolated context. They have no direct access to the DOM, which prevents them from interfering with the UI. Instead, they're designed for computational tasks like parsing, processing, or transforming large datasets. Inside the worker, you have access to features like XML HTTP request for fetching data, set timeout for timers, and WebAssembly for running near-native performance tasks. However, you won't have access to browser-specific objects like window or document. Web workers come in different types, each suited to a specific use case. Dedicated workers are used for single-threaded background tasks specific to a page or script. Shared workers allow multiple scripts or tabs to share a single worker, ideal for shared state, or multi-tab communication. Service workers extend functionality by intercepting network requests, caching resources, and enabling offline support. For more complex scenarios, web workers can also spawn nested workers. Can also spawn nested workers to offload even more processing, effectively creating a hierarchy of tasks. By enabling true parallelism, web workers empower developers to handle resource-intensive operations while maintaining a responsive UI. They are a key solution for addressing JavaScript's single-threaded limitations. Web workers are incredibly versatile, offering solutions for a wide range of challenges in modern web applications. While before we focused on the broader problem they solve, here we'll explore how to make the most of them and avoid common pitfalls. One of the most impactful use cases for web workers is in applications where large-scale data processing is required. Parsing a multi-megabyte JSON file or processing data in real time can quickly overwhelm the main thread. By delegating this work to a web worker, we keep the UI responsive, even as the application handles intensive tasks in the background. Similarly, web workers excel in applications that rely on computationally heavy algorithms, such as encryption, video encoding, or running machine learning models directly in the browser. These tasks, which might otherwise cause significant delays, can be performed seamlessly in a worker. To implement web workers effectively, it's essential to design them with clear boundaries. A good rule of thumb is to delegate tasks that don't require direct interaction with the DOM. Web workers thrive when working on isolated processes like number crunching, file manipulation, or real-time calculations. For example, in gaming applications, workers can handle physics simulations or pathfinding algorithms, ensuring the main thread is free to handle rendering and input processing. However, web workers aren't a silver bullet. Managing their life cycle efficiently is crucial to avoid memory leaks or unnecessary performance overhead. Once a worker completes its task, it should be terminated to free up resources. Spawning too many workers at once can also strain the browser, as each worker has its own memory footprint and execution context. Balancing the number of workers with the complexity of the task is key to maximizing performance. Another best practice is to carefully manage communication between the main thread and the worker. Since web workers use post message to exchange data, minimizing the size and frequency of messages can significantly reduce overhead. For example, rather than sending raw data directly to a worker, pre-process it into smaller optimized chunks before passing it along. This approach not only improves performance, but also reduces serialization and deserialization times. Finally, debugging web workers can be challenging due to their isolated nature. Tools like Chrome DevTools make this easier by allowing you to inspect workers directly. Logging messages in both the main thread and the worker can help you trace issues and understand how data flows between them. By adhering to these practices and understanding the strengths and limitations of web workers, developers can unlock their full potential. Whether you're building a dashboard, an interactive game, or a resource-intensive application, web workers provide the required parallelism to keep your app fast, responsive, and scalable. At Yodeck, we've implemented web workers to power a feature we call the ticker, a marquee-style text scrolling display that needs to run smoothly across screens. This ticker shows dynamic content, meaning it can change at any moment. The main JavaScript thread handles updates by processing the new content and breaking it down into smaller, optimized pieces. Each piece of content is loaded as a sprite, which is essentially an image to be displayed in the ticker. Since the main thread also handles other logic for our player, we keep it responsive by offloading specific tasks to dedicated workers. We set up a two-worker system to divide these tasks equally. The main thread manages the application itself, moving sprites across the screen and partially uploading new textures to the GPU. This ensures smooth scrolling while efficiently handling resource-heavy tasks. The nested worker is dedicated to rendering text content. It loads the text and renders each segment onto an off-screen canvas before retrieving the byte data, which it then passes to the main worker. This approach keeps the main worker free to focus on managing the ticker's display elements. In addition to dedicated workers, we also use service workers to provide offline functionality. Offline playback is crucial for digital signage, as screens need to operate seamlessly even where there is no internet connection. Service workers function as a network proxy, intercepting requests made by the app and serving content from a local cache when the network is unavailable. During the initial setup or when content updates, the service worker downloads and stores all necessary assets in the cache, including images, videos, scripts, and other media files. This ensures that the player has everything it needs to function offline. The service worker continuously monitors for changes and replaces outdated assets in the cache while keeping the rest intact. This minimizes download times and bandwidth usage. When the player requests content, the service worker first checks the cache. If the content is available locally, it serves it instantly. If not, it retrieves the data from the network and caches it for future use. By managing these tasks, the service worker ensures a seamless playback experience regardless of connectivity. For example, in cases of intermittent internet outages, the screen continues to display content without interruptions. When a reconnection occurs, the service worker synchronizes with the server, ensuring the latest content is ready for playback. Combining dedicated workers for dynamic content management with service workers for offline functionality has allowed us to create a robust and responsive system. This approach not only improves performance, but also ensures reliability in the most challenging network conditions, which is critical for our customers who rely on uninterrupted digital signage. In closing, web workers are not just a solution to performance bottlenecks. They represent a paradigm shift in how we think about building modern web applications. By enabling through parallelism, they allow developers to take full advantage of the browser capabilities, ensuring that applications remain smooth, responsive, and capable of handling complex workloads. Throughout this talk, we've explored how web workers allow us to offload intensive tasks to background threads. Whether it's parsing large datasets, handling real-time calculations, or managing computationally heavy tasks, like image processing, web workers let us focus the main thread entirely on delivering a seamless user experience. This separation of concern results in apps that not only feel faster, but are also more resilient and scalable. Beyond the immediate benefits of performance and responsiveness, web workers also open the door to innovation. Imagine applications that previously seemed out of reach for the web, such as web-based video editors, 3D modeling tools, or real-time collaboration platforms. Web workers make this ambitious project possible, empowering developers to push the boundaries of what web applications can achieve. However, it's important to remember that, like any other tool, web workers need to be used strategically. Properly managing their life cycle, balancing worker usage, and optimizing communications are essential for reaping their benefits without introducing new inefficiencies. By following the best practices and leveraging tools like ROM DevTools, developers can effectively harness their power. Looking ahead, web workers continue to evolve alongside the web ecosystem. With advancement in browser APIs, we're seeing even greater opportunities to integrate them with technologies like WebAssembly for near-native performance, shared array buffer for low-latency data sharing, and off-screen canvas for rendering tasks. These advancements make web workers even more indispensable for building cutting-edge web applications. As you leave this talk, I encourage you to reflect on your own projects. What task in your application could benefit from the parallelism and efficiency offered by web workers? Whether you're solving existing bottlenecks or aiming to build something entirely new, web workers are a tool you can count on to bring your vision to life. Thank you very much.